In this video, we're going to look at another situation in which we get an EMF induced in a coil because of a changing flux, right? I didn't point out in the last video, this is called Faraday's law. And when I say Faraday's law, that means this induced EMF is minus N delta phi B delta T. This is Faraday's law. Make sure I have enough room to write this. Sometimes called Faraday's law of induction. This tells you that I'm inducing an EMF in some sort of coil of conducting material because I've got a changing magnetic flux. Remember, the N tells you how many turns of wire I have. The negative sign tells you that the induced EMF is going to seek to counteract the change in flux. So let's look at this situation. I have an apparatus which is completely encased in a magnetic field. This apparatus consists of two rails along which a conducting rail can slide. So everything here is a conductor. Now, this is in motion. This is some length L of my conducting rail, and then it's traveling at a steady velocity. V doesn't have to be steady, but in this case, let's make it a constant velocity. Notice what I have over here. In this region that through which the rail has already passed, I've got a closed loop. Therefore, if this is all of this is a conducting material, therefore I will have a magnetic flux through this closed conducting loop that is changing. Why is it changing? Well, the area of this loop is getting bigger as I drag this thing. Now, how am I moving this? I don't know. I could have tied it to some horses and set them running. It doesn't really matter. The point is I'm causing this thing to move, and that is creating an increase in magnetic flux through this loop. And so Faraday's law says that I will get an induced EMF in that loop. Let's see if we can characterize it. Okay, the change in flux. What is the change in flux? Well, first of all, what is the flux? Right? The flux is the magnetic field. I'll write this down. Flux is the magnetic field times the area of this loop. What is the area of this loop? Well, it's a rectangle. One side is L, and the other side is changing, but at any given point in time, I can characterize it as delta X. If I'm starting over here at my origin, then it has moved a delta X. So that is actually my flux. Notice that the area of this loop, if I form the area vector, it's going to be perpendicular to the plane of the page. So is the magnetic field. So I can leave off the cosine of theta here. It's just 1. This is the area. And so this turns out to be the magnetic flux. Now, how does it change in time? Well, I can say that delta phi delta t, can you notice that this actually is a change in flux? I should do that here, sorry. Yeah, this is a change in flux because I've got this delta x. The flux at any point would just be x, but because I wrote delta x, I'm recognizing that the x is changing and therefore the flux is changing. My apologies for that. This is delta phi, BL, delta x. In other words, this is basically how the area changes. Yeah, sorry. So delta phi, in this case, is B times delta A. There's no delta B because B is constant, but there is a delta A, and that is L delta X. All right, fair enough. If I do this then, that's going to be BL delta X over delta T. Fair enough. Well, look what we have here. If I just do a little grouping, delta X over delta T, I hope we still recognize that as the speed of this object. That is the speed of the bar here. So it looks like I can just rewrite this as BLV. Now, according to Faraday's law, this has got to be equal to the negative EMF. All right, remember Faraday's law, E is equal to the negative N delta phi B delta T. N here is just one. I've got just one coil, and so N just really doesn't appear, and all I did here is move the negative sign over. But what I've done is I've calculated the magnetic flux, and that's going to be equal to the negative of the EMF. So if I were to ask you what EMF is induced in this coil, if you know the field, if you know the length of that rod, you know the speed, that turns out to be the magnitude of the EMF, which is probably what I'm going to ask you for anyway. We usually typically throw away this negative sign and account for it when we account for our direction, right? So the magnitude of the EMF induced is just going to be BL, V, where V is the velocity of the bar. Now, let's do the hard work and figure out the direction. So ask yourself, is the flux changing? Yes, it is. We've already determined that. Is the flux increasing or decreasing? Well, it's increasing because I'm getting a larger and larger area. And let's keep in mind that it's increasing due to a field pointed into the page. So if it's increasing, what does nature want to do? Nature wants to decrease it. How can nature decrease the flux from a field into the page? The answer has to be that nature induces a magnetic field pointed out of the page because she wants to decrease it. Okay, so what does it tell me about my current? Use my right hand rule for fields. Thumb in the direction of what's straight. In that case, that's coming towards the camera out of the page. My fingers then tell me the direction of the current. So it certainly looks like in this case my current is flowing this way. Counterclockwise, if you will.